So let me briefly remind the algebraic geometry approach to what would be super Yang-Mills. So after some preliminaries, we agreed that we should consider the algebra A. That should be DGL. And this A is a product of the algebra of functions on R10 times polynomials of lambda and theta, where lambda and theta have 16 components. Both lambda is even, theta is odd. But it's not just this. So it's not all. This is factorized by the ideal generated by gamma quadrics of lambda. So sometimes people write it in this form. Equation lambda gamma I lambda equal to 0 corresponds to so-called pure spinors. Okay? 1 second. Once again, this is commutative associative algebra, supercommutative associative. To get DGL, we need to multiply it by some Lie algebra. So this already forms DGL. And this is an analog of well-known theory called generalized Chern-Simons, where supercommutative algebra, associative algebra, is the algebra of differential forms on some manifold with some differential D. So I forgot to say what is differential here. So it's not an algebra, it's DG algebra. So differential here, I call it Q, in order not de confuse it with de Rham differential, is this. Plus and I call this Q1 and I call this Q2. Also, this Q has another form. I called these vector fields S tilde alpha. It was important that S tilde alpha form so-called supersymmetry algebra. It means that they supercommute just as these elements. And it is not a surprise because this S alpha may be considered as left invariant vector fields on supergroup. Okay, since there are left invariant vector fields, there should be also right invariant vector fields. And right invariant vector fields should commute with left invariant vector fields. So it's easy to, okay, sorry, tilde. So it's easy to write them in the following form. Minus okay. Now, so how to see that they commute on the level of formulas? The crucial thing is this minus sign. When you supercommute, this term that comes with minus is cancelled with this term that comes with plus. All this allows us to consider the analog of the covariant extension. So, of course, you remember that if you have that in the covariant case, when we had differential D and we had a vector field IV, we could form this object that squares to 0 on invariant forms. And later on, you see this epsilon is even because IV corresponded to the odd symmetry. Now we can play the similar thing, play the similar game. So we consider Q plus epsilon alpha S alpha. We will call it Q epsilon. However, this Q epsilon does not square to 0. It's easy to see that this Q epsilon squares to epsilon alpha, gamma alpha beta I, epsilon beta, d or dxi. So it doesn't square to 0. However, there is some interesting case where it actually squares to 0. It squares to 0 where? So it's foolish to ask d over dx to vanish. It would not be that interesting. It's better to ask this to vanish. And we already know this condition. It is a condition that epsilon is pure. Well, now let us see how we can study what comes out. When I say what comes out, I want the following. Here we clearly see bicomplex, two differentials, that anti-commute. So,
Q or 1.
Sorry?
Epsilon is Q or Q plus epsilon.
Epsilon is even. So actually, we would like to do the following. We would like to go to, in order to understand the system, it's good to go to cohomology.
So Q epsilon is Q epsilon Q plus or Q1 plus.
Q plus.
So the full Q. Okay.
Full Q.
I see. Okay.
So here is Q. You see, I was not hearing you clearly. So yes. We have Q1, Q2, and I add Q of epsilon here.
Okay. Okay.
So let us see what happens if we go to cohomology of Q1. So it is clear that since function on R10 are not involved in Q1, cohomology would be functions on R10 times something, some vector space that I'll call H. In quantum field theory, we will call H is what is called polarizations. And it comes from the electromagnetic theory. When we write connection as A mu of X, mu is called polarization. So it's interesting to compute cohomology of Q1. In order to compute cohomology of Q1, it's better to see its geometrical meaning. And interestingly, it turns out that it has clear geometrical meaning. So we have a complex acting on this space. So this is differential, and this is the space. Okay. Properly, people write down differential after. And it's interesting to see whether this complex is something that we already met in algebraic geometry? And the answer is yes. This complex we already met in algebraic geometry. And the meaning of this complex is the following. It is so-called Tor complex. Let me remind you what is the Tor complex. Suppose we have a ring, R ring. Okay, I'll call it ring in order not to confuse it with R. And suppose we have two modules. Arbitrary modules. We would like to have derived tensor product over ring. We do it in the following way. We can either replace M1 or M2 by a complex of, say, 3 modules. So sometimes people say projective, but in our case, it's enough to consider 3. So what would happen if I do this? Then I can take either C1 tensor over R M2 or M1 tensor over R, okay, ring of C2. Now here I have differential that I'll call D1. And here I have differential that I'll call D2. So this is a complex. And this is a complex. I can also do C1 tensor C2 with differentials D1 and D2 acting here. So the total differential would be D1 plus D2. So I have 3 choices. And the general theorem says that cohomology of each of these 3 complexes are isomorphic. And when we consider such complex, we can go from one cohomology to another, and it's called tic-tac-toe.
Sorry, can I ask a question?
Yes.
How does the CI complex is related to MI? I mean, is it completely? It cannot be completely arbitrary, right?
No, it's called cohomology.
No, that should be quasi-isomorphic. Okay,
Okay.
I'm sorry. So when I say replace, I meant exactly this.
Okay, so it's kind of a resolution.
Yes, it's exactly a resolution.
Mm-hmm. Okay, thank you.
So now we need to talk a bit about resolutions. And here, the important issue is so-called Kazul regularity. Of the set of functions. So set of functions is called Kazul regular if we can do this, the following thing. Suppose we, okay, I'm thinking how to explain it. You see, basically, this condition is about the transversality. So it's enough that if they are transversal, or as we will see,
So that means you have enough differential to generate a tangent space.
yes, but even more general things could be Kazul regular. So they are actually Kazul regular if, okay, so I will not go into detail of Kazul resolution. I will say the answer. The answer is that they are Kazul regular if the resolution is a external algebra. So let us see the example of Kazul regular complex. Okay. But before I'll do this, before I explain this, let us see what we actually have here. So here we actually have the following. So what is it? It is actually C of lambda over I. Here we have ideal generated by this, and this is of course module M1. And we also have C of lambda theta with a differential lambda alpha d over d theta. And this, what I would like to call C2 complex. So first, let us see that this is a resolution of the complex of the module C of lambda, and here we have ideal generated by lambda. Actually, this thing is C. So it means that lambda is acting by 0 on this module. So now, why this thing is such a resolution? So it is clear because differential says that all lambdas are exact. Now, we may understand C of lambda theta in the following way. It is an external algebra. So it is C of lambda times theta alpha C of lambda. Here we have some alpha from 1 to, in our case, 16, but etc. So it means that this is free, this is free, and the resolution is an external algebra. Okay. So this is the structure of this module. However, we need, so in order to compute it, it's better to use the theorem that I mentioned, namely consider resolution of M1 to understand what could happen. So let us try to construct this resolution. And more generally, let us try to construct resolution for the module C of lambda factorized by such ideal. There is a way to do this. Let us try to start this resolution term by term. So of course, first, we need to have this C of lambda. Now, we need to say that Fi's of lambda are annihilated. So we have a vector space generated by something. I'll say the basis here is xi times C of lambda. Now, what could be a differential here? Differential should take this psi of I. It's better to say that we have a vector space, and vector space is span of psi I. And differential here should take psi I to Fi of lambda. So, so it is the first term. we need to go further. So how can we do it? We need to write something that should kill cohomology that appear here. And here the main thing is the following notion as syzygies. I think it's
No, actually, they all should be Ys. The rest,
all should be Ys.
yes. Well, yeah.
So what are syzygies? Suppose you have set of function of lambda. Syzygy, so unfortunately it's called also by S. I'll call them by D. Consider the following equation. Equal to 0. So it's equation on D. And it's clear that is a module over C of lambda. Actually, I can multiply it by any function of lambda. It will still be a solution. Now, this di, so now let us look how this di could look like. So it is kind of easy to find the simplest solution to this equation. The simplest solution to this equation is di of lambda is epsilon ij fj of lambda. So I can put here even lambda. Really, if you multiply, so this epsilon, you see, I wrote it as epsilon, assuming that it is antisymmetric in ij.
So what is V2?
Sorry?
Why is not
So here is the sum of a j. So if I substitute this d of lambda here, I will get epsilon ij fi fj, and it is 0. Because this product is symmetric and this product is antisymmetric. So there are two cases. First case is, so I call this d epsilon, or it's better to call it dA in order not to mix. Constructed using antisymmetric tensor. So first case could be that DAI actually form a basis. Now there could be two cases, and there could be a second case where D does not form a basis, that there are other syzygies that are below this. So you see, these syzygies. So just imagine that all Fi's have the same degree. Let me call it degree K. In the case that we will consider, this K seems to be 2. Now, if these DAs, so sometimes these DAs do not form a basis. So there are other D tildes, in particular of lower degree.
Sorry, so what is the index A here?
So it's not A,
IA.
it stands for anti-symmetric.
Oh, okay.
So you see, I wanted not to put here epsilon. So it's for anti-symmetry. Okay, so if DI form a basis, I mean this one, I can consider V2 made out of antisymmetric tensors of the second rank. In this case, V2 would be nothing but the second external power of V1. Now, let us see what would be the differential here. Differential here I already explained. Now I need to explain differential here. It should take epsilon ij to what? To something that later on would go to 0, because this has to be a complex. So clearly, this is a complex. We can take this element, go here, then go here, and it will be 0. But very important thing is that if these DAs form a basis, then this complex does not have cohomology here. So it is a resolution. However, if they do not form a basis, we have cohomology here. So it means that our resolution would not be external. It will be something else. And it is interesting that in the case of super Young-Mills, the second possibility takes place. So these dA do not form a basis. Now, before we would proceed, let us try to see what would happen in the so there are two cases. Case that is considered regular is when they form a basis, and similarly, we could go further. Lambda 3 of V1, etc. Case when we have such resolution is called Koszul regular. Otherwise, it's called Koszul irregular. So it is clear that if Fi's are lambda alphas, lambda or linear things, it is Koszul regular case. And we have already seen it. However, we are not interested in linear things. We are interested in quadrics. So let us see the strategy. If we form a resolution of this module, we would have, so we have this resolution of this module with some differential, and this is, of course, some complex tensored by C of lambda. And we will multiply it by C of lambda over the ideal generated by lambdas. In this particular case, it is easy to compute. So the answer would be for cohomology. So here we will have no differential at all. So answer would be just V star. Because in taking a tensor product, I'll have to put lambdas to 0. Now imagine what would happen if Fi's of lambda is a set of casual regular quadrics. Okay, in this moment, according to our rule, I will take a 5 minutes break, okay? Okay. So let me try to continue. So in the case, if I'll have a Koszul regular case, I can do the following. I can write this tic-tac-toe box. And this tic-tac-toe box, so I can do it in any case. But let me tell you what tic-tac-toe box gives you. Here we have cohomology of first differential. Here we have cohomology of the second differential. And tic-tac-toe box allows us to take cohomology of the first differential, go along this box, and come to cohomology of the second differential. So it means that we should be able to see this external algebra in the cohomology of the original complex. And in this case, I can easily, so in the regular case, this could be easily written down explicitly. Once again, in the regular case, the cohomology are the following. Of course, complex numbers, we can call it zero cohomology. First cohomology is theta gamma I lambdas. Okay, so when I say quadrics, so just imagine that here I have not so Fi are quadrics. So it's better to write it in the following way. H2 and so on. You see, here we see this operator, theta d over d lambda. Actually, the meaning of this theta d over d lambda is that theta d over d lambda is homotopy of lambda d over d theta inside the tic-tac-toe box. So once again, when we do tic-tac-toe box, we do the following. We construct a bicomplex that has zero cohomologies everywhere here. So inside, we should be able to inverse both operators. In particular, this thing inverts lambda over d theta. Actually, if fi has some degree, I have to divide by the degree. So strictly speaking, I have to divide by 2. It's because theta d over the lambda, lambda d over the theta, is of course lambda d over the lambda plus theta d over the theta. So this is a degree. And here degree is 2. But this is a detail. So these are representatives of cohomologies obtained by resolution of this module in the tensor complex. It is clear that they are closed. So let us check it. That these are exactly what we have, what we need. Just apply lambda over d theta to this product. So it is clear that it's proportional to fi. And that's why equivalent to 0. So these are cohomology. Now, just imagine that we have the following differential Q for regular case. Q, that once again is lambda over d theta plus just imagine this. Imagine. So instead of considering actual case where these f's is made out of gamma quadrics, we consider this model. Then what would be? Cohomology would be external algebra of psi i's. So I call this psi I. And now this thing would be psi I over d over dxi. And then Q, not Q1, but Q on cohomologies of Q1 would be the RAM operator. So, because you see, this expression is just what starts here. And we would start with such construction and land to what we call Chern-Simons. So it's important to see that Fi be regular, the outcome would be Chern-Simons-like theory. But it is not what we want. And actually it happens that it is not the case that we consider. By the way, here is a good question. And good question is, remember that such construction would also have supersymmetry. Minus something similar to this. Sorry, here something like second derivative. And you may ask how this supersymmetry that are built in such construction are acting in Chern-Simons, because Chern-Simons is definitely, so we don't see any supersymmetry there. So it's kind of a puzzle. And the answer is clear. In this particular case, S alpha just annihilate cohomology of Q1. So yes, in the regular case, Chern-Simons actually is supersymmetric, but with zero action of supersymmetry. Then you may ask, how could it be that because we assumed that there was a full supersymmetric algebra, right? So if supersymmetries act by zero, what about supersymmetric algebra? And the answer is that in this particular case, d over dx, that is commutator of supersymmetry, also act by zero. So that's what happens if we consider a regular case. So in order to get something interesting, we should consider casual irregular case.
Sorry, Andrei, I think I'm completely lost. So with this differential Q is supposed to be the differential of the bicomplex. So, right? So corresponding to this, doing both resolutions on both sides of the Tor, right? So, I mean...
Okay. So maybe I went too fast.
Yeah.
Thank you,
so at least I don't understand the second term, how it appeared.
You mean this one?
Yes.
You see, I intentionally say that there are two things. Okay, maybe I went too fast. So...
No, first one is the Cazul differential for the quotient of C lambda by ideal generated by lambda, right?
Yes. No. Okay. Once again. So I said that we have Q1. Okay.
Mm-hmm. And that corresponds to doing a free resolution of C somehow, but written
Yes.
as a, yeah. Mm-hmm.
Yes. Yes, it corresponds to it. But
Mm-hmm.
now I would like to see the cohomologies themselves.
Yes.
I'd like to see how they look like.
So the cohomology of what? Of which differential acting in which space?
I would like to see the cohomology of Q1 acting
Mm-hmm. Mm-hmm.
on, of course, this. Here I put FIs, okay?
Okay. Mm-hmm.
And the claim is okay, I'll go slower. That if Fi form so-called Cazul regular sequence, then these cohomology are isomorphic to external algebra of size. But it is better to go further, to see their representatives.
Yes.
And how do we attribute? So what are their representatives? So in order to construct their representatives, once again, I need to use this tic-tac-toe tool. So I take cohomology at one place, and then I need to go along tic-tac-toe machine. In the tic-tac-toe machine, I have to invert.
Sorry. No, I'm sorry. I mean, you're saying something standard about spectral sequences, but I don't remember. So, what is it that you're saying? So, what are the elements in this table? So, they are tensor products of what?
They are tensor products of what? So I have
Of
two
elements of the two resolutions, right? So
Yes.
on both sides.
Yes, there are elements of the two resolutions, and one resolution is given by differentials that I was writing.
Yes.
That were called D, and these corresponded to syzygies. Another differential was also corresponding to syzygies, but of the skyscraper module. And for me, it is convenient to write the second differential that stands here as lambda over d theta. So there are two differentials. One is syzygies, and they have some vector indices. Another is this. And when I go from cohomology of the syzygy complex to cohomology of Q1, I need to take inverse of this lambda over d theta. Actually, homotopy.
Yes.
So actually it means that in this passage, I need to apply these operators that are homotopies inside this tic-tac-toe box, because theta d over d lambda is a homotopy for lambda d over d theta. And then I can see the images of the external algebra. So I have external algebra and I'm moving down. So this is a general theory. But you see, it's a general theorem. I'd like to write down some representatives.
Yes.
So let me see what comes out. So what is this external algebra if I write them in terms of lambdas and thetas? And here is an answer. They are external products of such expression. And what I did, so what can I do? I can, in particular, explicitly check that they are closed. So how do I do it? Of course, I act by differential. And I see that they actually belong to the ideal generated by Fi's. So theorem says that I have not missed anything. That I have not missed any cohomology. Okay. Now, let me play this game. Let me continue to play this game for the regular case. Because before we try to see what happens in singular case, let us play the full game in the regular case. So, in the regular case, we can try to write down analog of Q. That would be plus so this would be Q1 and this would be Q2. We can easily understand the meaning of this. This is actually the first cohomology of Q1. So this differential, so not only it's a differential, it also has a meaning. Let me remind you that in the theory of the Ram differential, so it's analogy. We sometimes form such differential for closed omega, for closed and odd. Okay, it's called Novikov differential. So if we consider these as constants, this Q is kind of a Novikov differential. So once again, it's analogy. Okay, let us try to see what would be the, so in this model case, regular case, the cohomology of Q1 would be external algebra generated by xi times the function of xi. So what would be Q2? I can induce Q2. In this particular case, Q2 would be, you see here I just multiply something by a generator of the external algebra. Xi I d over dxi. Okay? Now, I can interpret this cohomology of Q1 as space of differential forms, because I have the same number of xi i's as the number of xi's. So these are differential. These would be differential forms on the space X. Now, what would be the meaning of Q2? It is clear it would be the round differential on the space X. Okay? Pasha, do I have a proper speed now?
Sorry, I don't have a properly working head, but it's all good. It's all good.
So, for the regular case, I would get Chern-Simons type theory. So I promised you that there will be polarizations, and these polarizations would make functions of X just differential forms. So it is polarization, and Q2 would turn out to be the round differential. So sorry for going too fast. Now, I want to make an important remark. It is remark on, I put it in like this, supersymmetry. Because in this particular case, quadrics, there is an analog of supersymmetry. One can imagine. So just imagine that Fi are some gamma tilde I with coefficients alpha beta. Then similarly to the original case, there will be differential operators that would commute with Q. So I may think about supersymmetry written in the same way. Minus Oh, sorry. They would commute with a differential. So one may ask a question. How could it be that there is kind of a supersymmetry for Chern-Simons? And answer is that everything, namely S alpha and d over xi, act by zero on cohomologies, but not of Q1, of Q. Because this S alpha commutes with a total Q. But that's what we know in the case of Chern-Simons. No supersymmetry and differential act by zero on cohomology. Because cohomology of Q would be equations of motion. So this completes the regular case. So regular case is nice, but not that instructive. That's why if we think that we can get something interesting, we should consider irregular case. And what is interesting is that there are not so many irregular cases. You might try to look for irregular cases, mostly you'll find some stupid answers. But let us see what happens in the case where gamma tilde is not the matrix for regular quadrics, but actually a gamma matrix. Now we come to real case, okay? So let us try to write down this resolvent. So first term is standard one. Well, this is V. It is nothing but it depends on the field. So it is actually R10. So instead of R10, I'll write it as 10. So it is a physical notion. Here it's definitely a representation of SO10. So theory is SO10 invariant. So everything has to be SO10 representations. Now, in the regular case, here I'll have 45. However, there is an interesting relation that happens for 10-dimensional spinors. And if we look at this relation, we see that this is not quadratic, but linear syzygy. This term is linear in lambda. So it immediately means that we are losing regularity, but it's good. Since we are losing regularity, what we will have here?
Oh, more generators.
So it means the number of generators would be actually less. So I can call it 1. So here I have 10, and here I have 16, because once again, here syzygies are parameterized by this spinor index alpha. And the number of spinors is 16. Now, if I schematically write down elements here, namely their representatives, as lambda theta, these elements would be not lambda square theta square. They would be lambda theta square. And the reason for this is that in the tic-tac-toe, we obtain representatives by acting by theta d over d lambda. And if relation is linear and not quadratic, we would not get another power of lambda. So let me tell you what is the complete resolvent here.
But wait a second. So we don't. I mean, in the regular case, there were kind of all the the whole symmetric, anti-symmetric
Yes.
exterior algebra, and here I'm surprised that you're saying that we need less generators. So you're saying that those generators are
functions. So
are already generated by these ones, or no? I don't understand.
Yes, they are generated by these ones as C of lambda modules.
So I'm confused about, okay, there is, I think, this terminology of Kazul-Tate resolution and when you need to join the state generators. And I thought that this is exactly what you're doing.
So, you see, so of course, epsilon, so of course, here there are also quadratic syzygies, but they do not form a basis. No, not only they do not form a basis, they could be obtained from these syzygies that have degree 1.
I see.
So it's not 16 replace 45. It is 16 times 16 replace 45. So I told you that syzygies could be multiplied by any function of lambda.
Yes.
So in order to get previous antisymmetric solutions, we should multiply it by lambda. So we have a freedom to find the 45 inside 16 times 16. So there is enough room for it.
Yes.
So surprisingly, here I would also have 16. So I will not show things. So people studied that. And structure here is lambda square times theta cube. It means that here we have something quadratic. Now here it happens that we have something that we have again 10. And here we have expression like lambda square theta to the fourth. And finally, we end up with lambda cube theta to the 5. And here we have this magnificent line. So it has 6 terms instead of how many, 10 or something. Instead of 11 or 12. Instead of 11, I think. Oh no, instead of 10. So degrees go from 1 to instead of 11 terms. So 0, 1 up to 10. And this is remarkable. What we can do then? We may identify. So these are polarizations. So we need fields. And what is this additional spinner? They look pretty much like antifields. But it's not all. Now, we need to look for two things. First thing, action of Q1, or of Q2. And what is even more remarkable, we need to look for the higher action of Q2. So I say it in advance because, Pavel, I know that you are a bit tired. So instead of surprising you, trying to keep you awake, okay? I will tell you well where to look for. Okay? So it is clear what happens here. It is external differential. So it has a gauge symmetry. So here I'm considering the action of Q2. And what I have here, Pasha, let me ask you this to see that you are awake. How I'm multiplying by lambda theta d over dx. This thing is has degree lambda theta, and this has degree lambda theta squared. What would I have here?
Mm. I'm not sure.
0.
Mhm.
Here I
Yes.
have 0
Yes.
because here it's linear
Yes.
in lambda.
Yes.
Surprisingly, here I have 0.
Mm-hmm.
So here I have something.
Mm-hmm.
So what could be a natural differential that acts between two spinors, that preserves, that is compatible with the Lorentz invariance, and that is first order in
And
derivatives of x?
Dirac operator?
Exactly. There is no other choice. So similarly here, we have 0. Similarly here, we have something like, I don't remember, D star or something. So it's not that important. Maybe D. Actually, D star, I think it's D star. Okay. So this looks almost like super Young-Mills. But actually, it's not super Young-Mills. Because here we have gauge symmetry, here we have Dirac operator, but we don't have Young-Mills equation of motion. But if we think just a bit, we would see that we cannot get them from the action of Q2 itself. Let us recall that Young-Mills equation of motion, at least Maxwell equation of motion, starts from this. So it is a second order
Mm-hmm.
differential operator. So of course, if we restrict Q2 to cohomology, we cannot get second order differential operator.
Mm-hmm.
However, now we know a bit of homological algebra.
Mm-hmm.
And we know how we can get it. We can get it as a higher induced operator. You see, it's interesting that homological algebra actually helps in understanding super Young-Mills. So before we see that algebraic geometry helped us a bit, and now it's homological algebra that helps us a bit. So what can we expect? We can expect this operator. So Q2 has derivative in x. I would not be lazy to write down Q2 again. So having 2Q2 makes the day. The only thing I need to care about is that I actually have a room to play. So Q2 acting on lambda theta term brings something that is lambda squared theta squared. It is not in cohomology, but it's good. Because I do not want to get to cohomology. I want to get to something exact. Just to apply Q1. So Q1 goes like lambda d over d theta. Q1 minus 1 goes in opposite way. It grows power of theta, and it lowers power of lambda, right? So from this place, I go to something that is lambda theta cube. And then I apply Q2 again. Now it grows power of lambda and it grows power of theta. So I land exactly here. Okay, so when I land exactly here, I need to ask the following question. What is the second order differential operator that is Lorentz invariant and also gauge invariant? So how do I know that it should be gauge invariant? It is because induced action of Q2 should be a differential. That's why it has to be gauge invariant. That's why this thing is exactly d star d. So there is some coefficient here, and the only equation would be that this coefficient is 0 or not 0. So at least I hope that I made it possible that it is. So I think now I need to make a 5 minutes break, right? And I'm leaving you inside this, how to say, algebra geometry and homological algebra and super Yang-Mills. But before I say that it is super Yang-Mills, let me make a remark that now, you see, I explained this. It has the proper space of fields, almost. The space of fields is actually doubled. But what is interesting?
Because of antifields, or why double?
Because of antifields.
Yes. Mm-hmm.
They are where the fields should be. But what I'd like to mention here is that now, in this irregular case, we have a room for supersymmetry to play. Because supersymmetry now is d over d theta plus theta d over dx. And supersymmetry perfectly well acts here. Not like in the case of Chern-Simons, of regular sequence that we described before.
So without homological algebra, we cannot get Yang-Mills, super Yang-Mills.
No, you see, let me put it this way. Without homological algebra, we will have to do like people did, a long, tedious calculations.
Yes.
Saying this equals to that, this equals to that, and it was absolutely not clear what is going on.
Right.
And these calculations were done by Edward Wheaton, first by Nelson, then by Edward Wheaton, then by Verkovitz. But what they were missing are two things. They were missing both algebraic geometry and homological algebra content. You may say that it's not algebraic geometry. You may also say that it's homological algebra. Okay. So when I speak about Kazoo, I would say, okay, it is homological algebra. So only homological algebra. So this is an interesting example how homological algebra is working in supersymmetric physics. Okay, so now I'll make a 5-minute break. So Pasha, was it 5 minutes that have passed?
Sorry, I was not looking at the watch.
I was also not looking. Okay.
Yeah, it probably was. Mhm.
Okay.
Mhm.
So I think now it is 5 minutes.
Mhm.
So after all these preliminaries,
Sorry, before we start, can I ask one question?
sure.
So we said that Q2 is kind of acting from C to A with differential, and then from A to psi with 0, and then from psi to psi star with the Dirac operator, right?
Yes.
So if we would consider kind of the square of Q2,
Square of Q2 is 0.
but so this would mean that acting on psi, like the Dirac operator squares to 0 in this case, or?
No, that's going by Dirac and then by 0 is 0.
Ah, okay, yes, absolutely. Oh, sorry, yes. Okay, thank you. Sorry, I got confused there. Sure.
So now, so actually what we got right now, we got the action of, in this way, we got only actually Maxwell equation.
Mhm.
But
as
we would like to get super
Yes.
Yang-Mills equation,
So we
not
need
just
higher
Maxwell.
operations. Mhm. So we need higher products.
First, we need products.
Mhm. Mhm.
So I told you that the original space of fields was not just this supercommutative algebra, but something multiplied by the Lie algebra.
Yeah.
So we can have a product here. That is, of course, L infinity, actually Lie product. Sorry, DGL product. That is coming from multiplication here and commutator here. That I call M2. So, starting from the equation of motion like this, or actually it's better to write it like this.
Mhm.
We need to do the following. We need to consider this as an L infinity structure with two operations. So this is M1 and this is M2. And we would like to go down to cohomology of Q1. So, of course, we have M2 restricted to cohomology. And here we have Dirac operator coupled to the gauge field. And this is not surprising. Not surprising. But it's interesting to see what are other things that we get. So that's one thing that we get from M2. Another thing that we get from M2 is, of course, gauge transformation. So it comes from commutator of C and A. Also not surprising. What is interesting is how are we going to get Young-Mills equation, not just Maxwell equation? Because let me remind you that Young-Mills equation is, of course, this. So actually, here we have curvature. So if we write it in terms of fields, we have this structure. We also have such structure, and we also have double commutator structure. So how do we have it? And actually, of course, we get it just by writing diagrams. So let me denote Q2 by such operation. Then I am claiming, and let me denote M2 by such operation, as I already did.
So there's something wrong with, I mean, with the structures. I mean, like for instance, in the quartic one, if you put the star the way you did, it's 0 by degree reasons. It should be bracket of A of comma star of bracket A with A.
Why it is 0?
Because A is a 1 form, star A is a 3 form, and A is a 1 more form. So you get a 5 form on a 4-dimensional. Sorry, it's not 4-dimensional, but anyway, then in a 10-dimensional space, you would have 1 form and 9 form and the 1 form.
What I just want to say is that we understand that Maxwell is like this.
Sure, sure. No.
And when we say covariant derivative, we replace this by D plus A. And
yes.
Take a commutator.
No, it was just star in the wrong place, I think. It should be star of the bracket.
Yes. Like this. Okay, so actually what we do the following. And let me also introduce the homotopy. So the Maxwell equation is written like this. Now, to get Young-Mills, we just have to replace this by this with A coming from one leg. So we actually have the following higher operation. So this is M2 induced, and this is M3 induced.
Mhm.
Okay, so it is homotopy here. So that's how we get super Young-Mills. So together with the so this is super Young-Mills coming out of homological algebra.
Mhm.
And now, so we got it. Now we need to think about supersymmetry. So we need to denote supersymmetry somehow. So when we speak about supersymmetry, it's better to say that we have Q plus epsilon alpha S alpha, and now epsilon alpha are not necessarily pure spinors. And this is the ghost for translations. So when we go to cohomology of Q1, we are not touching these epsilons and L's. They are external. So what is this? I can depict it with some other symbol. So let me use this symbol as as a square with epsilon inside.
Sorry, when you add this new third term, then does the whole thing square to 0?
Then everything squares to 0.
Mm-hmm.
Because it's R. Sorry. So I need to add this for translation. So all this is external.
Mm-hmm.
So now I have this interesting epsilon. And of course, I have this for the action of supersymmetry.
Sorry, Andrei, why does it square to 0? I mean, we had a problem before.
Because
What?
because as alpha, sorry, I had to tell that. Because as alpha and d over dxi form the supersymmetry algebra.
Mm-hmm.
And here I'm adding this term. So it's a standard BRST construction.
Okay.
So,
No, sorry. Then maybe it should be.
okay,
Should be
I have to write it in a bit different way.
No, but Andrei, so maybe it should be not Li star, but d over dli. Did you confuse the differential with the dv action?
Okay. So you're right. So for you're right. If I'm trying to write it as a differential, I have to write it like this.
Yeah.
And if I'm trying to write it down as an action, I have to write like this. Okay, here I write B.
Mm-hmm.
Yes. So this is BV action. And this is differential. So here I have this new operation. Okay. And then we can see two things. First, we see that this operation actually goes down to cohomology. So first we have such structure. Also, we have this structure. So how do we know that we have both of them? We know that we have both of them because we know that supersymmetry contains terms that have derivatives and that have no derivatives. Okay?
So H means homotopy.
Yes. So this is induction of supersymmetry. So just think, how can we get supersymmetry with derivative from this structure on cohomology of Q1 if supersymmetry involves derivative? It could be only homotopically induced structure.
So all this else.
Sorry, so what is
sorry.
okay, please. So what is H? Sorry.
So H is, and here we come to an interesting issue. H is homotopy.
Okay.
For Q1 that acts between that inverts it for the lambda theta square term. So for lambda square theta square term. So we know that we had cohomology here. So this stands for degrees. And also here. But we have no cohomology in this degree. So if something hits here, we know that there exists homotopy. Unfortunately, it's not possible to write it down very explicitly. And this is actually the main problem of this approach. We know that there is a homotopy, but we cannot write it explicitly, and this is actually the main problem that Berkovits has. I'll come to this issue a bit later, but at the moment, I just want to show you how supersymmetry acts.
Sorry, Andrea, I was confused. So now this everything, the space on which the differentials act is extended by these LIs?
Yes.
Mm-hmm.
But you may say that they are external. So when we write, so you may say that we may ignore extension by x. Yes, but we are not. So we consider them as an external data.
No,
So
but
it's
you're
better-
right. You're writing an input and an output for this epsilon box. So input and output. It seems that there's a derivative in Li going there.
So epsilon here,
Mm-hmm.
epsilon here, is the action of S tilde alpha on cohomology of Q1. Sorry, it's on the complex, not on cohomology. On the complex.
Oh, so it's not that quadratic term in epsilons. I see.
So this operator acts here.
Mm-hmm. Okay.
It acts by derivative. So, okay.
Ah, no, that's good. Okay.
So it acts here.
Mm-hmm. Mm-hmm. Okay. Okay. Good.
So we can either restrict it to cohomology. It's interesting.
Mm-hmm.
And we see that in some cases it was possible. So I think it happens when we go this way. Okay, so here we act without or all the way around. So it's d over the theta. So d over the theta piece. So sorry, I said something wrong about extended things. So this S alpha contained two pieces, d over d theta plus theta d over dx. So d over d theta was acting in this way. And it is not acting from psi star to psi. So here it's not acting. I'm sorry. So when I said for homotopy, but it also is acting in the opposite way. Here. from lambda theta to lambda theta square with derivative. And of course, you see, it does not involve mixture between ghosts and fields. What I wanted to say is that there is also higher action of supersymmetry. Namely, there is such structure. That contains two epsilons. So let us try to see where this structure could come. So it is higher structure, higher action of supersymmetry. Let us once again write this complex. Lambda theta squared, lambda square theta cube, lambda square theta fourth, lambda cube theta 5. So, as far as I remember, we would be interested only in this piece. You can check that higher is not acting. So, let me try to remember. I think it goes like this. You start here. And first you consider d over d theta. And then you go to lambda square theta square. Then you consider Q1 inverse. So Q1 inverse is something that I schematically can write as theta d over d lambda. So it brings this term to lambda theta cube. Okay? And then I take a derivative in theta again. So higher supersymmetry acts here. So I have the term that is kind of surprising term. That is quadratic in epsilon. But from what I told you before, we should expect it. Because this term would eventually lead to the bivector or to infinity realizations of supersymmetry. Let me recall that in the infinity realization of supersymmetry, we have action plus so here I'm writing again and again this infinity realization of symmetry. So this infinity realization of supersymmetry that was theoretically predicted by BV language says that VA-VB is not, okay, so plus ghosts is not just FABC VC, but also pi IJAB DJS. So it's called on-shell symmetry. And it is interesting that this on-shell symmetry in simpler models could be obtained by eliminating so-called auxiliary fields. So in some sense, going to cohomology is like integrating out, in this case, infinite tower of auxiliary fields. And you see, we start to have such structure. Now, there are several important issues that I have to add. And these issues are,
Sorry.
yes?
So what is exactly this epsilon operation?
So this epsilon, so in this case, this
Yes.
epsilon operation is d over d theta alpha epsilon alpha.
Okay.
And if you combine these two things, you will get something like, so it's a linear operation. So in the action, you will get psi star, but it's not a B field. It's field that I got here, or psi. So it goes from psi to so it's an operation that is quadratic in epsilon, and it contains some combination of gamma matrices inside. So it has no derivative, but it is quadratic in epsilon.
Okay. So higher means sometimes
Higher
take
means quadratic in epsilon.
yes, we also take this inverse operator like Q1 inverse.
Yes, exactly.
And
from the description of cohomology and homotopy, it's computable.
I think higher, yeah, there's the standard notion of an L infinity module. So here fields form
Yes.
an L infinity module over the supersymmetry
Yes.
algebra. Mm-hmm.
Yes. So, but in this case, yes. So L infinity symmetry is an L infinity module. So what is important, what I would like to say is that symmetry is realized as L infinity module, yes. Supersymmetry is realized as L infinity module, and it is kind of physical realization of this formal algebraic structure. Now I need to do, so at the moment it was what I'd like to call BF theory, because it was B QA plus M2AA. And when I moved to cohomology, I got, of course, I don't know how to call it, maybe small letters. B M1A plus M2A plus M3A. Okay, maybe I'll write it in this form. But as we discussed last time, it is too much. This is not super and Yang-Mills. It is a square of in Pavel's terminology. Because we have, so this is BV action. So it is too much. We want to, as Pavel said, to take a square root out of it. In order to take a square root out of it, unfortunately, so we need a BV structure. A BV symplectic form on cohomology of Q1. Surprisingly, we do have it. It is because our resolution had interesting form. And we were able to pair it this way. You should not be mistaken that such pairing always exists. Yes, in the Cazul regular case, we have one d minus 1 over 2, etc. And we end with d minus 1 over 2. It's powers of external algebra. And in Cazul regular case, this pairing was not surprising because it's a pairing in external algebra. However, here it is very far from, it's not clear how did this pairing came out. So it's a problem that I don't understand. Namely, here, I studied different irregular sequences. And you may check that in general case, the resolution does not have such symmetry. In other terms, I do not know. It doesn't mean that it's not existing, but I do not know the pairing here. I do not know the pairing that goes down to cohomology. Because what I know, that if I put here not gammas, not regular, but something irregular, but arbitrary, such pairing does not exist. But in this case, for a reason that I don't understand, you may consider this as an empirical reason. So this is the reason. So this reason seems to go beyond homological algebra. There is such a pairing. So sorry for small b. Yes. And we may go from this action to the action that contains only A. And here is this pairing. So sorry, I put here, I should put here M1, not Q. Okay, it's Q, but it's better to write it as M1. And this is super Young-Mills in D equals 10. That is a maximal supersymmetric theory that does not contain gravity. I want to say another thing about it. Namely, this construction has an interesting but not understood generalization. And this generalization is, consider D equal 11. Now dimension of spinors is 32. We need to take both left and right. And consider similar construction. Absolutely similar construction. Where mu goes from 1 to 11. So it's again set of quadrics. And differential is the same. Exactly the same. Mu goes from 1 to 11.
Andrei, so you previously said that to have a symmetric pairing on spinors, you need something like some very particular dimension, like
Yes,
4,
but
10.
now, yes, but it was on the while spin, on the left moving of the, sorry, of the left spinners.
Mm-hmm.
And here we consider all. Dimension is 11. So we
Yeah.
consider both left and right,
Mm-hmm.
both chiralities.
But so the quadrics, they pair only left with left and right with right, or what do they do?
Yes.
Mm-hmm.
Pairings pair left with left and right with right.
Mm-hmm.
And gamma 11, as you know, is just 1 on left and minus 1 on right.
Mm-hmm.
So now alpha, okay, goes from 1 to 32. And if you study such system, so this system is understood only on the linear level. So on the level of operations M1. So it's interesting that on the level of operation M1, it is nothing but 11-dimensional supergravity. And if you just think about structures,
How can it
That-
be on the level of M1? You can only get a free theory.
yes, linearized.
Yes,
Linearized.
but 11-dimensional supergravity is probably something very complicated and nonlinear.
Yes, yes, but it has, but you may consider it above the flat background.
Mm.
So when we speak about Lorentz symmetry gamma matrices, it's reasonable to talk about the flat
Mhm.
background. So linearized above the flat background.
Mhm.
And this is a great mystery. So it's interesting that you know that 11-dimensional supergravity has a 3-form potential. And this 3-form potential has an interesting structures of symmetry for symmetry, etc. So there are functions, 0 forms that go to 1 forms, that go to 2 forms, that go to 3 forms. And there is something else that happens. So here we have something like d star d. So this line of differentials for the 3 form could be understood partially from the fact that you have something regular up to the level 3. And only on the level 3 you start have something irregular.
Yeah,
So
yeah,
actually-
that looks very much like the sort of complex for Maxwell theory.
For the Maxwell theory,
Mm-hmm.
you have this,
Yeah, yes.
but here you already have this.
Yeah, it's just a bit longer than for the Maxwell theory, yes.
Yes. So, but you see, it's longer, But from the point of view of homological algebra, it means that you keep regularity far enough.
Mhm.
That in some place you have regularity that is far enough.
Mhm.
So it partially explains something, but still it's a mysterious. So the resolvent is very huge, very high, very long. And it was checked that it is like this. And also, I don't remember this resolvent, it also has this symmetry property.
Mhm. Mhm.
And let me finally comment on the problem that Berkovits has. So we know that cohomology of Q1, sorry, that cohomology of Q belong to the light cone. Because these are the space of solutions to Maxwell equation and Dirac equation. They belong to the light cone. So the question is how to understand it.
So I don't know, what does it mean belong to the light cone? So I mean, light cone is, I mean, there's no comparison really. I mean, there are functions on the light cone, or
No, cohomology of Q are functions of
what?
on.
Yes.
So when I say that it belongs to, so these functions could be decomposed in the Fourier series.
Yes.
And it is known that cohomology of Q are zero if pi square is not zero. So this is known. However, so you may expect, so let me compare this with okay, no. Okay, so
Okay,
so
I see.
one may expect
I see. Okay.
that there is homotopy
Mhm.
that looks something like this.
Mhm.
So it means that if p squared is not zero, such homotopy exists. You see, I intentionally put question marks
Mhm.
because it's a wishful thinking. And it would be nice if this would be differential operator. So would it be like this? One may look for pure spinor particle. Times something. So this would be called pure spinor particle. Particle because we have p squared here. But as far as I understand, such particle was not found. And that's a problem. So for Chern-Simons-like theories, homotopy is d star over d star d. And this is Laplacian. And that's why here we have Chern-Simons particles. And here we don't have such particles. So it's interesting that existence of such particles and the non-existence of particle here is a question of gauge fixing.
Sorry, I have absolutely no idea. What do you mean by particles?
By particles, I mean so why I'm writing such expression? I'm writing such expression because this comes from the integral. So you may write it differently. So the best way how to write it. So I'll take m squared equal to 0, but particle is this. So this is a Unbane. So if you integrate P and E out of it, you will get this. Or you may have an intermediate form. Just integrating out P, you will get something. So this is Polyakov expression for particles. So if you have particle, you can consider particle propagating in Schwinger time up to t. And if you integrate over Schwinger times, you get propagator. Maybe now I'm going too fast. I think it's, so I will not going to discuss this particle issue, okay?
Okay.
Okay, thank you. I'm a bit tired, so I need to say goodbye.
Thank you. Thank you.
Yeah, thanks a lot for the lecture.
And Pavel, you see, I have to go to the doctor today. So I am not sure that I'll be able to.
Okay. So
I let you know.
Okay, thank you. But when you're writing, please, could you write to everyone who should be there?
Oh, okay. You see, I have to go to the doctor, so I'm sorry.
Right.
See you.
Okay, bye.
Okay, thanks a lot. See you.
Thank you.
Bye.
Thank you very much.